Hello, everybody. In this video, we are going to talk about how to generate embeddings. The first technology you explore is embeddings, which address the first issue of encoding data into a representation that captures semantic meaning. Although multimodal data, including text, images, audio, video, and code, can be converted to vector embeddings, let us use text embeddings as an example. The challenge is, again, how to represent text in a numeric format while retaining its meaning. This challenge can be further divided into two subproblems. One, how do you turn text to numbers that retain meaning? For example, the numbers should indicate relationships between words such as similarity and difference. And two, how do you turn text into numbers that can be fed into a machine learning model? For example, a machine learning model normally requires the input to be a relatively dense matrix or vectors. An overly sparse matrix might lead to model overfitting. Any ideas for how to resolve this? Let's talk about text representation techniques to set the stage for vector embeddings. From simple approaches to state-of-the-art techniques including basic vectorization and word embeddings. Let's start with the basic vectorization techniques. For example, an intuitive technique called one-hot encoding. With this technique, you one-hot encode each word in your vocabulary. Consider the sentence, "A dog is chasing a person." After tokenization, which divides the sentence into smaller digestible units, and pre-processing, which leaves the root and keywords, the sentence can be represented by three words: dog, chase, person. Assume you have a vocabulary that includes 6 words: dog, chase, person, my, cat, and run, which can easily be tens of thousands. You then place a 1 in the position that corresponds to the word and zeros in the rest of the positions. By conducting one-hot encoding, you tune each word to a vector and convert the sentence, "A dog is chasing a person," into a matrix that a machine learning model ingests. What are the benefits of one-hot encoding? It's intuitive to understand and easy to implement. However, let's also acknowledge the disadvantages. Recall the two sub-challenges of text representation. One-hot encoding has two main issues among others. First of all, this representation does not convey any relationships between words. Second, the generated matrix is high-dimensional and sparse, which leads to overfitting of the machine learning model. What does it mean? The dimensions of each vector depend on the size of the vocabulary, which can easily be tens of thousands. Also, most of the values of each vector are zeros, which means that this is a super sparse representation. Imagine you have 10,000 words in the vocabulary. You can create a matrix where 99.99% of the elements are zero. This results in a large, sparse matrix, which can lead to computational waste and model overfitting. To solve these problems, you explore a new approach called word embeddings. Let's start with intuition to see how you can encode text to numbers that convey meanings using word embeddings. Let's ask the question, how would you describe a dog? How about their breeds, physical stats such as height and weight, hair color and length, relationship to you such as a family member or neighbor's dog? Their behaviors like bark or quiet, you get the idea. You can easily think of at least 20 different dimensions to describe a dog. How do you describe a word then? For example, the word Paris. How do you convey the location, history, culture, continent, art associated with this word by using quantitative measurements? You can use dimensions and in math a vector space. You can now generate an idea. How about representing a word in a vector space with dimensions to describe its properties? Not only that, you want the distance between the words to indicate the semantic similarities between them. For example, Paris and Tokyo are close to each other, but far from Apple. Additionally, you want this representation to capture the analogy between words. For example, the distance between Paris and Tokyo is similar to the distance between France and Japan. Now you have Paris minus France plus Tokyo equals to Japan. Isn't it amazing to play with words in the same way you play with numbers? Word embedding is a technique to encode text into meaningful vectors. The technique lets you represent text with low-dimensional, dense vectors. You don't need the vector size as big as 20,000 like in one-hot encoding. Instead, you have between single-digit dimensions for small datasets and four-digit dimensions for large datasets. Each dimension is supposed to capture a feature of a word. A higher dimensional embedding captures detailed relationships between words. However, it takes more data and resources to train. Additionally, you don't have sparse vectors anymore. The cells of a vector in word embeddings normally contain values. More importantly, the vectors capture the relationships between words where similar words have a similar encoding. Word embedding is sometimes referred to as distributed representation, indicating that the meanings of a word are distributed across dimensions. You now understand the idea of word embedding. But how can you develop such an encoding system to convert text to vectors? Instead of manually specifying the values for the embedding, you train a neural network to learn those numbers. Neural networks have been used to train word embeddings, which include a variety of algorithms or models, such as the popular word2vec by Google, Glove by Stanford, and FastText by Facebook. To learn more about the different algorithms used to train neural networks to generate word embeddings, please refer to the module on text representation in the course titled Natural Language Processing on Google Cloud, which is listed in the reading. Training on a large corpus typically requires a great deal of computational resources. Fortunately, you do not have to train the neural networks yourself. Instead, you can use pre-trained embedding models by calling APIs. Consider the following code example to see how simple it is to use embedding APIs. After importing the embedding libraries, you first need to specify the name of the pre-trained embedding model that you want to use, such as text embedding Gecko and multimodal embedding, both provided by Google. Second, you need to define the text input. Third, you need to get the embeddings. You can find more coding examples in the following demo and the hands-on lab. You have examined text embeddings. You can also use the same approach to convert other media, such as images, to embeddings. This way, you can find that the text dog and the image of a dog are located near each other in the same vector space. Thank you for watching. Please check out the next lesson about creating vector search.